Hello and welcome to another Mathematical Moose video. Today, we're going to talk about, why everybody always tells you to not gamble. All of your parents, your teachers always tell you, don't ever bet money, because you're going to lose it. But why? Sometimes you think that, there are people who win. For example, sometimes I win if I bet some money. I can get it back if I bet correctly. But the thing is, we're going to prove a theorem today that states that every persistent gambler goes broke. Now, to clear a few things up here, there's persistent, which states that even if you win, you're going to bet again. So, what this theorem actually says is that if you continue betting, no matter how much you win, you still want to bet more, then at some point, you will lose all your money. First, we're going to go through an intuitive explanation of this. Then, we're going to prove it mathematically. So, let's say you start with K dollars. So you're over here. And you bet some of it. Now, let's say you win some of your money back with probability P. Then you go up. Hooray, you have more. But you're going to bet again. And so you start with this money, and you continue betting and it could go up or it could go down. So, what if you lose some amount of money and go maybe to a few dollars? But what if you lose again? Then you could go to zero. Now, you might think that, okay, you're just going to have a random amount now because you're going up and you're going down. But the problem is, no matter how much up you go, you can always go down. But if you go down to zero, you can never get back up because you have no money to bet. And that is why this theorem makes sense. Because at some point, if you ever reach zero, you will go broke. But even if you reach $1 billion, you can still go broke by gambling and gambling. So now let's describe our game. We are saying that with probability P, we win K dollars. And we say with probability 1 minus P, we lose $1. Now, why is this general? You might be thinking that, how much do we bet? But the thing is, the betting amount doesn't really matter. We can set it to 1, but all that matters is the probability of how much we win and the probability of how much we lose. And also, why can we just say we lose $1? Well, let's say we lose some amount L. Okay, and we win some amount W. Then you can divide everything by L. So this gives 1, W over L, which we're replacing by K. So now that we can assume this without loss of generality, we can start our proofs. Now we need to define what our expected value function gives us. E of x is the expected value of our money after infinite turns starting at x dollars. So if we use this as our definition, we have that E of x is equal to, we start with x dollars, and on one turn, let's go back here, with probability P, we win K. So, if we win with probability P, so P times the expected value of, we just won K dollars. So, our money goes up from X to X plus K. And if we take the expected value of this, starting with infinity minus 1, or infinite turns still, then that's E of X plus K. What if we lose? Well, that's going to be 1 minus P probability times E of X minus 1, because we would lose $1 and stated here. Now we're going to use a very common trick in expected value. Let's write a few of these out. So starting with E of 0, we can use this equation since X minus 1 will be negative 1. But we already know that E of 0 will be 0 because we're already broke. So, what about E of 1? Well, Year 1, now we can use this, is P of E of X plus K. Which is just going to be K plus 1. Plus 1 minus P E of 0. Now, E of 2 is equal to P of E of K plus 2 plus 1 minus P times E of 1. And we are actually going to continue this till infinity. Well, what happens when we take the sum of all of these? We get that the summation from x equals 1 to infinity of E of x is equal to P times the summation of x equals K plus 1. Because this goes K plus 1, K plus 2, dot, 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 to infinity of E of x. Plus 1 minus P of summation of x equals 0, since this goes E of 0 to E of 1 to E of 2, to infinity of E of n. We're going to leave this first term and second term untouched for now, and focus on the third term. We're going to take x equals 0 out of the summation. So this is going to be E of 0 plus 1 minus P times summation of x equals 1 to infinity, because they took the x equals 0 term out of E of x. Okay, now moving like terms over to one side, we see that the last term and the first term both have summation from x equals 1 to infinity of E of x. So we can move it to one side, and we get 1 minus P times the summation of x equals 1 to infinity of E of x, and equal to P times summation of x equals K plus 1 to infinity of E of x, plus, well, what is E of 0? We already showed up here that E of 0 is 0. So 1 minus P times E of 0 over here should just be equal to 0. So this is our equation. Well, 1 minus P is just P. So we get this equation. Dividing out by P, we get that the summation of x equals 1 to infinity of E of x equals the summation of x equals K plus 1 to infinity E of x. Well, up here, we had something similar. We had x equals 1 to infinity and x equals 0 to infinity. Here we have x equals 1 to infinity and x equals K plus 1 to infinity. So we can write the left-hand side as x equals 1 to K E of x plus x equals K plus 1 to infinity E of x. But this is equal to x equals K plus 1 to infinity of E of x. Okay, so we can cancel these two terms and get that the summation of x equals 1 to K E of x is equal to 0. Okay, now this is very interesting because the E of x, the expected value of money you have, is always greater than or equal to 0. Okay? It can never be negative because once you're at 0, you don't bet any more money. So this value always has to be greater than or equal to 0. But if the sum of non-negative numbers is equal to 0, then every single one of those numbers must equal 0. So for x equals 1 dot 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 K, E of x must equal to 0. Okay. we've got this. Now, what we're going to do is we're going to repeat our first step. What was our first step? Our first step was writing out all of these values and then what we did was we summed them all up. But instead, we're going to take e of k plus 1 is equal to e of 2k plus 1 times p plus 1 minus p times e of k. Then we're also going to take e of k plus 2 is equal to p of e of 2k plus 2 plus 1 minus p times e of k plus 1. And we're going to take this to infinity again. And if we then take the sum, we get summation of x equals k plus 1 to infinity of e of x is equal to p of summation of x equals 2k plus 1 to infinity of e of x plus 1 minus p times, we're going to take out the e of k, plus summation of I of x equals 2k plus 1 to infinity of e of x. Now, what we do here is we know that e of k is equal to 0. So, we can remove the e of k and just take it, the summation, from now we know e of k is equal to 0. So I could just take the last part and completely remove the e of k. So this is just summation of x equals k plus 1 to infinity of e of x. Now moving like terms, just like last time, we get that p times the summation of x equals k plus 1 to infinity of e of x should equal to p times the sum of x equals 2k plus 1 to infinity of e of x. And dividing out by p, we get that the summation of x equals k plus 1 to infinity of e of x is equal to summation of x equals 2k plus 1 to infinity of e of x. Now, we can again split this into two parts. This is just x equals k plus 1 to 2k of e of x plus summation of x equals 2k plus 1 to infinity of e of x. So, this must equal to the right-hand side. Now we can cancel like terms again and get that the sum, this has to equal 0. But just like last time, this is always going to be non-negative integers. And thus, we get that for x equals k plus 1 to k, e of x equals 0. And to continue this, you can just use induction, and using the same exact strategy as we have, you prove that for x greater than or equal to 1, you get that e of x must equal to 0. And so, because we know that if you start at $0, you're also at the expected value of $0 after infinite turns. That means that every persistent gambler always has an expected value of $0 at the end. And so, they will be broke. So, what we have learned is trust your parents on things. Thanks for listening.